Hi, welcome back to Structural Analysis Made Fun and Easy. So today we're looking at this couple roof. So a timber couple roof consists of Durapitch roof, but on this roof, as you can see, there's no collar ties, and there's no ceiling joists, so which are used as ties. So basically it's unsupported. That means the walls are taking the thrust, because when you push down on the top of the roof, the rafters will spread, and the only thing holding it up is the walls. So the walls have to stop it from. That's why it says span from 3 to 3.5 meters. Seems like there's nothing they can do really, sort of like to make that span bigger, because it's just, unless you've got really massive buttress walls, it's going to be putting big forces on the walls. So the couple roof consists of rafters, and it's supported by the walls, not by the wall plates. The wall plates transfer the load, but they don't support it. And the ridge piece doesn't support the rafters. The rafters are leaning against each other, so that's why you've got compression in the rafters. The wall plate, which supports the rafters and transfers the load from the rafters to the wall, so I agree with that. The ridge piece is just tying the rafters laterally, and the rafters are connected to the wall plate by a bird's mouth joint to prevent the side end of the rafter. So if we've got span 3 to 3.5 meters and the other parts of it are the ridge board. Like sometimes you can have a ridge piece with the ridge clay tiles, rafters, and banders. Banders with 300. So now we can go to my diagrams. So we're starting with the shear diagrams. We're starting with the bending moment diagram. So this is what I had for my bending moment diagram for that roof. So we just got two like simply supported rafters sagging like this. So I just told you through what I've got. So this is a roof section, part 1, referred to the architect's plan, Bonner's Farm, Structural Developments and Innovation. That's the company name I got. We've got maximum moment, the span of the member. So we've got two sagging moments. The span of the member is actually this dimension, which is cos of half of the width of the roof. So cos 35 equals the half of the width over the length of the span of the diagonal span of the rafters. So the diagonal span of the rafters is equal to cos 35 times half the width, and the ridge board is just holding them up. That's not doing anything structurally. The maximum moment at the midspan of the members. This is my diagram that I use to help me work it out. So then I've done the width of the roof is 4.726, maximum bending moment and midspan of the rafter. Refer to the following calculations. UDL is applied to the rafters via the battens. Diagram 1. So the width of the roof on horizontally is 4.727. 35-degree roof. That means the span of the raft is 2.883. The height of the roof is 1654. UDLs are applied to the rafters via the battens. Maximum bending moment and midspan of the rafters, just like this. So then we go to, I tried to do the bending moment. See, refer to the unit load data sheets. The unit loads are dead load 1.5 kilonewtons per meter squared, and the live load is 0.75 kilonewtons per meter squared. The spacing of the rafters is 0.4 meters. So the UDL characteristic is dead load 0.4 times 0.15 times 1.5 is 0.6, and live load 0.4 times 0.75 equals 0.3, so it's 0.9 kilonewtons per meter. The maximum characteristic moment is M max clear is 0.9 times 2.9 squared divided by 8, it's 0.94 kilonewtons per metre. Kilonewton metre. So that sounds about right. That sounds about alright, doesn't it? 2.9, so 3 metres spare. So luckily that's alright. So that was. Then I've come back here to look at the stress in the rafters, the bending moments and the stresses. Sorry about the presentation, but calculation and check. Sigma x equals my divided by I, 50 200, and the rafters are 50 by 200. And so ix equals bd cubed over 12, 50 times 200 to the power of 3 divided by 12, see diagram 1, that's this one. So 50 times 200 joists at 400 centres, the ixx equals 33,333 times 33,333,333.33, 33.34 times 10 to the power 6 millimetres to the power 4. Zx equals bd squared over 6 equals 33.34 times 10 to the power 6 divided by 100 equals 3.334 times 10 to the power 5. So the stresses are, sorry about the presentation, sigma xx equals 0.94 times 10 to the power 6 divided by 33.34 times 10 to the power 6 times 100. So that is 0.94. Oh, yeah, 94, isn't it? 94 divided by 33, that's 2.819 newtons per millimetre squared. So we reckon that C24 has 7.2 newton per millimetre. This is only rough as well. It's okay in bending stress. Yeah, because the maximum, let's say it was C16 and sigma xx would be 5.3 max, sigma x applicable, sigma xx max was my over ix, so sigma that would be 5.3, so m maximum applicable would be ixx times 5.3 divided by 100, and so I reckon that would be 1.77 kilonewtons per metre. Kilonewton metre is maximum for a C16 joist, and we got 0.94, so we're okay. So I reckon that was alright. I haven't applied the load factors. So now we're on to the shear stress. So again, I think that the shear stress will look like this. On the rafters, it will be RA will be max, and then at the ridge it will be max, and it will be equal but symmetrical. The rafter will be 50 times 200 rafters at 400 millimetre centres again. Just the vertical combination load 1 shear forces. And so the maximum shear stress is 1.5 times the maximum shear stress is 1.5 times the maximum shear force divided by A. The maximum shear force diagram, that's 2.9. Sorry, it's drawn really badly. I'm going to redraw this. The standard design shear forces are, because we know the UDL, the DL is 0.6 kilonewton meters and the live load is 0.3, that's 0.9, so the maximum shear force is 0.9 times 2.9 divided by 2 equals 1.305 kilonewtons, is 1305 newtons. So shear max is 1.5 times 1305 divided by 10,000. The area of the section is 50 times 200, which is equal to 5 times 100 times 10 times 2 is 10,000. So the shear maximum is 0.19575. The allowable is 1.62, therefore since 0.1958 is less than 1.62 newtons per millimetre squared, that's okay. And the shear stress diagram looks a little bit like that. It's very sorry about the presentation. I'm going to redo this whole, but the section passes the shear stress check. Now, we seem to be missing the actual force here. Oh, there it is. It's a bit further on. Now we're checking deflection. Again, the span of the member is actually this dimension, which is 2.9. The maximum deflection of the member is at the mid span. We've got two reactions at A, HA and RA, and at RB we've got RB and HB. Checking the deflection of the rafters. Remember that the member is simply supported. Visualize the rafters as horizontal. Long span, low load. The maximum deflection I've put is 5 times WL to the power 4 of 385 EI plus the shear deflection, which is minimal, so we've ignored it. Therefore the dead load is 0.6 and the load load is 0.3, the tail is 0.9. Therefore 5 times 0.9 times 2,900 to the power 4 divided by 384 times E times I is IX. So that allowable E is 10,800. The total deflection is 5 times 0.9 times 2,900 divided by 384 divided by 10,000 divided by 33.34 times 10 to the power 6. It was 2.48 millimetres. Allowable is 2,900 divided by 360 is 8.06. The section passes the deflection checks. So that looks alright. What I haven't done in this was just checking the timber members. What I haven't done is I haven't checked the wall. I haven't checked the walls that the walls can carry it, because I haven't worked out HA and RA and RB and HB. That's what I need to do in the next calculation. So this is the axial force. The compression force one is the diagonal line in both directions. Roof section part 1 referred to attached plan A4 SK205. Oh yeah, and I reckon the actual force is a 4.764 kilonewton, because I did an equilibrium diagram. So the total V is RA plus RA equals 2.9. Times 0.9 is 2.71. Then I won't go through this because I need to check this, but I have tried to work out the reactions so that I could get the actual forces. But I'm not going to go through that. I'm going to go through that again. But anyway, the actual force is 4.764. Section A is the shear force calculation. The sigma XX compression is 4.764 divided by 10,000, 0.476. Using reference to the BS standard effective length at all. So I need to check that. Now that I've got, wait a second. Now I need to check the combined strength. Oh yeah, the compressive strength allowable is 12.31 newtons per millimetre, and I've got mine as 0.48, but that is maximum. That's without. I need to check LE. I need to check the effective length factors. I haven't done that properly yet, so I'm going to come back. If I do the local shear check, taking 12 as a maximum, then obviously it works. Combined stress check for maximum moment, like if it's fully restrained and there's no deflection or eccentricity, then moment stress 2.819 newton per millimetre divided by 7.2. That's equal to or less than half, isn't it? Because it's less than 0.5 plus miles less than 0.5. That's equal to less than 1, so it's okay. So in theory, it's, apart from I haven't checked the LE properly, but other than that, it's looking reasonably alright. But I haven't checked the wall reactions as well, so I need to credit and reference W. Mackenzie and the Timber Designers Manual. The other thing I need to check is I need to check that the walls can take the horizontal reaction, which I also haven't done. So I'll try and check that as soon as possible and then upload. Sorry about this, I'm not feeling well, bad back and sore throat, so hopefully the next video will be better as well, because I'm just going to redo the presentation and draw it all up again. Hopefully that'll be a bit better then. Hopefully you still enjoyed the video. Please give me any tips actually. There's lots of things I can do to improve my video. I know it's bad, the presentation. Sorry about that, but I just want to put this up because I think it's really interesting. I've never seen like a coupled roof, like, you know, all the forces set out properly. Hopefully this has been some use to you, even if it just makes you get interested in looking at this. And then feel free to give me comments and tips and suggestions, as I want to try and find out what the reactions are, and then design the wall to take it. So obviously I think the wall's going to be struggling. A single leaf wall, I don't think it's going to work. It's got to be at least a cavity wall, and maybe like some buttresses. And hopefully I'll go onto that in the next video. Thanks for watching, and please tune in for the next video. Thanks.